The systems usually prefer the 2's complement format because of its accuracy. How can I represent the minus 53.5 here? I have the value, I will divide it into 3 parts. Please remember this word. The gap between 1 and the next normalized floating point number is known as machine epsilon. Hello everyone, it is Dr. Ravikumar YB. In today's session, let me explain you about the floating point representation of numbers. What is the meaning of floating point number? Let me distinguish the difference between the previous session's fixed point representation of numbers and floating point representation of numbers first. In this case, the floating point representation of numbers, there is no fixed length after the decimal point. In case of floating point representation of numbers, whereas in case of fixed point representation of numbers, only 4 digits are used. That is, only fixed number of digits can be represented after the decimal point. That is why it is called as a fixed point representation of numbers. In case of floating point representation of numbers, we do not have any restrictions over the length of digits that can be incorporated prior to the decimal point. That is why it is called as a floating point representation of numbers. If that is the case, let me tell you that it does not reserve a specific number of bits for the integer part or the fractional part. There is no restriction over the length of the integer part or the decimal part. Instead, it reserves a certain number of bits for the number called the mantissa or significand, and a certain number of bits to say where within that number the decimal place sits, called the exponent. If that is the case, let me call this as SEM, where S stands for sign, E stands for exponent, M stands for mantissa. So we have these types of fields here. This sign may be a positive or it may be a negative. So we have these types here. The exponent, e raised to the power of some value, whether it may be a positive or it may be a negative. This mantissa may be anything value, any integer part or any value that is 10, 20, 25, so on like that. If that is the case, let us see through the one of the examples in the next and subsequent slides. Here, the floating point number representation of number has 2 parts. The first part represents the signed fixed point number called the mantissa. That is this one. This is called as the first part. Which is the second part? This is the exponent. That is the second part designated the position of the decimal or binary point and is called the exponent. We have this here. This is called as the second part. Then we have the floating point number is always interpreted to represent a number in the following form. That is MXE. M stands for mantissa, X stands for exponent, representation of numbers, MXRE. If that is the case, we have a sign bit here, exponent bit here and the mantissa bit here. So mantissa 0 is beginning from right to left. So we have the value from 0 to n. If this is the case, 0 to n represents n plus 1 items, 0 to n minus 1 indicates n items or n bits I can represent. Here n plus 1 bits can be represented. So if that is the case, the exponent is called as in the biased form. This is called as a biased. That means it is not shown. Exponent bit. Then actual number is represented by in this format, that is minus 1 to the power of s S represents the sign of that. Then 1 plus mantissa, that is 1 plus m into 2 raised to the power of e minus bias. So this is the format in which we represent the numbers. We need to notice here that the signed integers and exponent are represented by either sign representation or 1's complement representation or 2's complement representation. As I have already discussed with you all, we can represent it in the form of a signed form or in 1's complement representation or in 2's complement representation, which I have already explained in the previous session. So the same thing can be used here to represent the signed numbers, whether it is a positive number or a negative number, that can be represented in any of the 3 formats, that is using the sign of that or using the 1's complement format or using the 2's complement format. But we usually, the systems usually prefer the 2's complement format because of its accuracy characteristic. So a floating point representation is more flexible. Any non-zero number can be represented in the normalized form of this, that is plus or minus this value 1 point B1, B2, B3, B4, so on up to Bn to the base 2. We have the number in the binary format. So I am representing it here in the form of this into 2 raised to the power of n. What is the meaning of that? Let me clarify you that plus or minus 1.10101010 is the number I have here to the base 2 into 2 raised to the power of n. What is the meaning of that? This can be represented further divided into 1.10101010 to the base 2 into 2 raised to the power of n. There is one more sign, that is minus sign. I can represent it as minus 1.10101010 base 2 into 2 raised to the power of n. What is the meaning of n here? N can be used to represent the bit position. What is that bit position? It is 0th position. This is first position. As you can see, this begins from 0 to n. So I can represent it as 0th position, first position, second position, third position, fourth position, fifth position, sixth position, seventh position. So 0 to 7 we have 8 digits here. So I can represent it as in the form of this, that is 1 into 2 raised to the power of 7. N is equal to 7 here, n is equal to 6 here, n is equal to 5 here, n is equal to 4, n is equal to 3, n is equal to 2, n is equal to 1, n is equal to 0. If that is the case, I can do it in this format. I can further expand it in this format. That is, this number can be represented in this format. That is 0. 0 into 2 raised to the power of 0. 1 into 2 raised to the power of 1. 0 into 2 raised to the power of 2. 1 into 2 raised to the power of 3. 0 into 2 raised to the power of 4. 1 into 2 raised to the power of 5. 0 into 2 raised to the power of 6. 1 into 2 raised to the power of 7. So we have these values in this format. Since I have this form after the decimal point, I can represent it as this format. 1 into 2 to the power of 0 is what? It is 0 into 1, it is 1. But we have the value which is representing after the decimal point, that is the fractional part. If that is the case, 1 by 2 raised to the power of 0 is equal to 1 into 1 divided by 2 raised to the power of 1. 1 into 1 divided by 2 raised to the power of 2. This is 1 into 1 divided by 2 raised to the power of 3. This is 1 into 1 divided by 2 raised to the power of 4. This is 1 into 1 divided by 2 raised to the power of 5. This is 1 into 1 divided by 2 raised to the power of 6. This is 1 into 1 divided by 2 raised to the power of 7. You will see that we have 1 here, but what is the value we have here? 0. So let me make it as 0 here. We have 0 here, so 0 here. So this is 0 here, so this is 0 here. So if that is the case, 1 into anything becomes anything. If that is the case, 2 raised to the power of minus 1. 2 raised to the power of minus 1. This is, what is this value? 2 raised to the power of 0. This becomes 1. 1 into 0 obviously turns out to be 0. If that is the case, 1 into 2 raised to the power of minus 1. This is 0 into anything, 0 this term, entire term. This term, 1 into 2 raised to the power of 8, that is 1, 2 raised to the power of minus 3 into 1. That is this term 0. This term, 2 raised to the power of minus 5 into 1. This term turns out to be 0, and this term turns out to be 2 to the power of minus 7 into 1. So if I add up all these values, what is the value we get? We get this value. That is the fractional part. The same thing is explained here. The same thing follows for positive number. If that is the case, we have the number system which can be represented in this form. This represents the sign for negative numbers. For positive numbers, this becomes 0. If that is the case, we have the exponent part with value like this. That is 0, 0, 0, 0, 0, 1, 0, 1. In the mantissa part, we have this digits, that is 23 digits. That is 23-bit positions are like this. This is mantissa in case of 32-bit format. And what is the length of this? This is, the length of this is 1, 2, 3, 4, 5, 6, 7, 8. 8 bits. This is 23 bits and this is 1 bit. So 23 plus 1, 24. 24 plus 8 is equal to 32-bit format. This is 32-bit format. If that is the case, I want to represent a negative number minus 53.5. How can I represent the minus 53.5 here? I have the value. I will divide it into 3 parts. First part is what? Mantissa. This is exponent. This is sign. In case of fixed point representation of numbers, we had 3 parts. One of the part was sign, and the other one is integer part, and the other one is fractional part. In this case, I will represent it in the form of mantissa, exponent and sign. If that is the case, what is that mantissa indicates? Mantissa is represented by this, that is 0.5 is represented by this number, 53 is represented by this number, and 1 is represents the minus sign. So if that is the case, let me calculate the value of this. 0, 0, 0, 0, 0, 1, 0, 1. If that is the case, what is the value of this? We move from here to here. Since we have minus 53.5, I can represent it as this format. If you look at this, we have the value 1, which is going to be hidden. The same thing, this is called as an hidden bit. As it is always 1, when it is normalized, suppose if I have a value that is this value, I will normalize it to, suppose if I have 3.009, I will normalize it to a number 3.1. 009 is almost equal to 3.100. I will normalize it to 1. So this is an hidden bit. So if that is the case, I will represent this number as this format, that is mantissa part and the exponent part. What does the exponent part stands for? If that is the case, we shall see how this number can be represented here. This is minus 1, that is 1, 1, 0, 1, 0, 1, 1. This becomes 1 because this is an hidden bit. So if that is the case, we have 1, 1, 0, 1, 1, 1, 0, 1, 0, 1, again, 0, 1, again. We have 1 here. I will represent the entire thing by 1. So I will call this as 1. So if I consider this in the form of binary representation, I will mark it as 1. How can I represent this 1? I will place a decimal point here. This becomes 2 raised to the power of 0, 1, 2, 3, 4, 5. So if that is the case, I will represent it as in this format. I have this value that is 10. If I place a decimal point, 1.101011, this is a point here, to the base 2 into 2 raised to the power of 5. Yes, it is 2 raised to the power of 5. We have the value varying from 0, 1, 2, 3, 4, 5. So we have 2 to the power of 5. What is this minus sign indicates? Since it is a negative number, I have the value minus sign here. So I will place minus sign here and point here. So if that is the case, I will represent the number minus 53.5 in this format. If this is the number that is minus 53, then how can I represent it for other numbers? That is also possible. That is also possible. How? Let me tell you that. Minus 10.5 is the value we have here. What is the value we have there? 0.5. That is going to be normalized. If that is the case, we have a minus sign here. That is the third part. And next we have exponent here. Then we have mantissa here. What is that mantissa? How can I represent the value 5 here? 0.5. That is the same thing applies here. 0.5. That is this 10, 10, 11, 00, 00, 00, 00, 00. So we have this value here for 0.5. What about 10? The value 10. Value 10 needs to be represented. How can I represent it? It has to be represented in some form. What is that exponent indicates? What is that sign indicates? This is an exponent and this is mantissa. If that is the case, how can I represent this exponent? This C here, observe here carefully. 2 raised to the power of 0 is considered here. 1, 2, 3, 4, 5, 6, 7. 5 and 7 are 1, 1. What is the meaning of that? 2 to the power of 5 is what? 32. 2 to the power of 7 is what? 128. What is 32 plus 128? 32 plus 128 is 160. This becomes 160, right? But what is that actually needed here? This is 53 here. If that is the case, what is the value we are going to have here? So the entire thing exponent is going to be normalized. How the hidden bit is going to represent? It is going to be represented by the normalized value 1. So if that is the case, the mantissa is indicated by this, that is the 0.5 value. 0.5 represents this value. Then 10 has to be represented. What is the binary value of 10? 1010 is the binary value of that. If that is the case, I have to represent it in the form of the exponential form. Exponential form. Then 10 must be represented as this format. That is, this is the binary form. That is, the binary form of 10 is this. But I want to represent this 10 in the exponent format. That is 1010. That is 1010 followed by zeros. Again, we have this number here. I have to represent this number with minus sign. If that is the case, I will represent it like this. Similarly, by doing all these calculations, I am going to get the value which is equivalent to this number with equivalent to this, and this number equivalent to this number. 10.5 minus 10.5. So similarly, we have the value where 001010 we have here, which is the 8-bit binary value of the exponent value, that is plus 5. 8-bit exponent value field is used to store the integer. That is, we have 10 there. We have minus 53 there, 53 there. So the smallest number which varies from this to this is this. As I have already explained you that minus 2 to the power of k minus 1 minus 1. That is this. Minus 126 to plus 127. What is the meaning of that? The value n varies between this. If that is the case, n must be greater than or equal to n, less than or equal to 127. If that is the case, the smallest normalized positive integer number that fits into 32 bits is this number. This is the smallest bit. That is 2 raised to the power of minus 126 into 1.000, so on till how many bits it has to be represented? It has to be represented by 32 bit. In this 32 bit format, what is the value of that? So totally we have 23 bits towards this fractional part. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So totally we have 23 bits positions here. So similarly we have 1 in the integer part, that is in the exponent part, and there is no negative sign here. So let me represent it is in the form of, this is the minimum value. What is the maximum value? I can represent it here. In place of this, I will place 1 as it is. After decimal point, I will count, replace all zeros by 1. So that becomes the maximum value of that. Then what is the meaning of that? If that is the case, we have the minimum value which is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23. What is the maximum value I can represent? 1.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That's all. These numbers are used here. So the first bit indicates 0. That means it is a positive number. If it is 1 here, it was a negative number here. Exponent part and mantissa part. This is the smallest number, that is this. What about the maximum number? That is this. Largest number. 0, all are 1s and all are 1s here. 23 bits, all 23 bits are 1. All 8 bits are like this and 1 bits like this. So totally we have 32 bit format to represent the floating point numbers. The gap between 1 and the next normalized floating point number is known as the Meson epsilon. Please remember this word. The gap between 1 and the next normalized floating point number is known as Meson epsilon. The difference between one number and the next normalized number is represented by the name called as Meson epsilon. We have a non-uniform spacing in the fixed point scenario. The non-terminating binary numbers can be represented in floating point representation. That is, example 1 by 3 is equal to this. Cannot be a floating point number as its binary representation is non-terminating. What is the meaning of this? We have the number 1 by 3 which is equal to 0.010101 so on till base 2. 1 by 3 is equal to same as 0.333 which is recurring. So that's why we are calling it as non-terminating point. It is not just a terminating, it is a non-terminating point. So that's why we have the number 01010101 so on till a non-terminating point to the base 2. These non-terminating binary numbers can be represented in floating point number representation, which cannot be a floating point number as its binary representation is non-terminating. That is. Then IEEE format we have, in this case we have mantissa in the first part, in the exponent we have second part, that is part 2, and in the third part we have the sign of that is part 3 we have. So the actual number is represented as I have already discussed, that is minus 1 to the power of sign into 1 plus mantissa into 2 raised to the power of e minus bias. So here S is the sign of that, this is the sign of that. What is the mantissa? M is the mantissa, this is the mantissa. Then what is E is the exponent value. E is the exponent value. Then bias is the bias number. What is that number we are going to mask? That is called as a bias. Furnished value, the number which is going to be changed according to our requirement, that is called as a bias. Then the sign bit 0 is positive for positive number, 1 for negative number. Exponents are represented by 1's or 2's complement representation. So then we have the floating point representation with these formats, that is half precision with 16 bits, where 1 bit is called sign bit, 5 bits for exponent. In the case of half precision, 1 bit for sign bit and next 5 bits for exponent. And the remaining 10 bits for mantissa. Similarly, we have single precision. That is, in case of single precision, we have 32 bits. That is, in case of 32 bits, we have 1 bit towards the sign bit, and then we have 8 bits towards the exponent, then 23 bits towards mantissa. That is in case of single precision. In case of double precision, we have 64 bits. That is 64 bits, double precision. We have the value, that is 1 bit for sign bit, then 11 bits for exponent, then remaining, what is the remaining? 52 bits for mantissa. Then we have quadruple precision. We have 128 bits here. One bit to represent the sign of that. Then we have 15 bits to represent exponent of that. Totally 1 plus 15 is 16. 128 minus 16, that is the rest, 112. 112 bits towards mantissa. What is the meaning of all these things? If I have 16-bit precision, I can store the value up to this. What is the meaning of this? This is a sign. Let me consider it as a minus. Exponent 5-bit, I can represent it by 5-bit. What is that 5-bit? Let me consider 01010. This is my number in the exponent part. In the mantissa part, I have 10 bits. What is the 10 bits? 0000101000. This is the number format I can represent. After decimal point, I have this value. Let me consider this as the exponent and mantissa. Between them, I have a decimal point. I have to represent it in the form of this. That is mantissa. That is 2 raised to the power of 0. 0 into 2 raised to the power of 0. As I have already told you, 0 into 2 raised to the power of 1. 0 into 2 raised to the power of 2. Then 1 into 2 raised to the power of 3. 0 into 2 raised to the power of 4. 1 into 2 raised to the power of 5. 0, 0, 0, 0. That is 2 raised to the power of 6, 2 raised to the power of 7, 2 raised to the power of 8, 2 raised to the power of 9. All are zeros. We have these values in the fractional part, that is after the decimal part. If that is the case, this becomes 1 by 2 power 0, 1 by 2 power 1, that is 1 by 2 power 3, 1 by 2 power 4, 1 by 2 power 5, 1 by 2 power 6, 1 by 2 power 7, 1 by 2 power 8, 1 by 2 power 9. If that is the case, again that calculates and turns out to be the value which is equal to this. That is how we represent the fractional part. And we represent the integer part, that is the exponent part. If this is the case, this turns out to be the value 2 power 0 into 0. This turns out to be the value 2 power 1 into 1. This turns out to be the value 2 power 2 into 0. This turns out to be the value 2 power 3 into 1. This is 0 again. 2 power 4 into 0. This turns out to be the value which is equal to, that is 2 raised to the power of 0 is 1. 1 into 0 is 0. This is 2. This is 0. This is 8. This is 0. Again, we have 8 plus 2, that is 10. We have 10 point some value. What is that value? That turns out to be the value which is going to be in the fractional part. Since we have a negative sign here, I will use 1 here to represent in the sign part, and the rest of the values like this. So this is how we are going to represent the numbers in floating point representation of numbers. So thank you very much. If you have come across any questions with respect to the representation of fixed point numbers as well as the floating point numbers, let me answer all of those questions in the live sessions. Thank you very much. Thank you one and all.